All right, I've got an aggressive agenda for today, which is not typically a good thing. I usually can't quite meet that agenda, but I'm going to try my best to do as many different kinds of problems as I can. I think that one thing that will help us here to do as many kinds of problems as we can is to use Mathematica to do the calculations for us. We are just focusing on setting up the integrals, which is the more important skill that you want to get out of this stuff in Chapter 8 anyway. I'm going to do some problems in the book here to start off with. If you've got your book, you can open up to page 447. There's a problem on the page number 19 that talks about the volume of sand in a shed, though I think there's a typo in the book. The way the book states it doesn't make much sense to me. So it's going to be a problem about mass and ultimately center of mass, though I think the book doesn't ask about center of mass. You've got this shed, or this storage shed. It's shaped like a half cylinder. Like this. You're told the radius of the shed is r. That distance right there, which of course would also be the same as this distance right here, so we have a semicircle along the side there. And you're told the length of the shed is L. So this distance right here, that is L. They use a lowercase l for that. They want you to calculate the volume of the shed, which you could do without an integral, of course, because it's half of a cylinder. The formula for the volume of the cylinder is pi r squared h, where h in this case would be L. You could do it with an integral too. Let's focus on part B though. The shed is filled with sawdust whose density as a mass per unit volume, so that would be an ordinary density, at any point is proportional to the distance of that point from the floor. I think that's where the typo is. I think you probably would want the density to be proportional to the distance from the ceiling, from the very top. Because then it's going to be more dense down at the bottom. That makes more sense to me, and I'm going to go ahead and assume that's the case. Ultimately, calculate the total mass of the sawdust in the shed, and I think I'd like to calculate the vertical coordinate of the center of mass in the upward direction, which I think I'll call a z direction this time. What about the mass? So anyway, again, so there's sawdust in here, which of course I can't draw all the pieces of sawdust. I think it makes more sense to be more dense near the bottom, right? You would think so. So I would say if y is the distance from the top of the shed, so this is going to be like a positive y-axis going downward, I would say the density is going to be proportional to that y instead of y going upward from the bottom of the shed is the way the book states it. I think that's probably a typo, though I didn't check the answer in the back of the book. Delta is going to be a function of y, and I guess I'm calling it y instead of z. I was thinking I was going to call it z. But let's go ahead and keep it with y. This is proportional to y, so it's k times y for some constant of proportionality. So this would be the volume density, mass per unit volume. I guess standard units would be mass per kilograms per cubic meter. K is a constant. K greater than 0 is constant. Okay, first things first, how would you find the mass of all the sawdust in the shed? Since the density is proportional to y, it's constant along horizontal slices, where y is constant. So that's the way you want to imagine slicing the shed up. Okay, and again, you're just using your imagination to do the slicing. Slice the shed up into thin horizontal slabs. That might look about like that. Since I'm calling this axis y, probably it would be good to call the height of these little thin slabs delta y. Or if we were doing differentials, dy. Let's go ahead and use the delta in this case, and we'll use Riemann sums. I think for the sake of time, I won't try to bring in differentials. So that would be the height of the thin slab. What would be its volume? Call it delta V. If it's real thin, even though it could be real long, it might have a very small volume as well. Delta Y is thought of as being small. Delta V is going to be thought of as being small. And effectively, even though it's not technically a box because the sides are curved, go ahead and pretend that they're straight. Treat it like a box. The volume would be base times height times length. Let's call the base there. Let's call it W for width right there. This is going to be W times L times delta Y. That's an approximation because it's not exactly a box shape. It's going to have a curved side, but it's close enough when delta Y is sufficiently small. That's the kind of approach that you take. So that would be the volume of the thin slab. How about its mass, which you might call delta M? Just take the density times the volume. It's a thin slab where Y is approximately constant. Go ahead and use this quantity, thought of as being a constant, for that constant value of Y, to give you your approximation to the mass. So this becomes, when you plug things in, W times L times delta of Y times delta Y. Okay, again, we got two deltas in here. The lowercase delta is the name of the function representing the density. Capital delta there goes next to this delta Y, that's the thin height of the slab. So the total mass, which you can just call M, and that's supposed to be a lowercase mass because we're not thinking about moments here, would be approximately the sum of these little masses, an approximation because we're not doing an integral yet. And we have an approximation there as well, so we add up things like this. Does that mean we integrate this expression? Well, yes, but make sure you get everything in terms of Y. Now, L doesn't depend on Y, but W does. So before you try to translate this to an integral, you've got to figure out how W depends on Y. You may want to redraw this sort of a head-on cross-sectional look. For a given Y, what is this distance W? You know the formula for the equation of a circle, x squared plus y squared equals r squared when you center it at the origin, and if the radius is r. W is kind of, well, W over 2 is kind of like an x coordinate. If this entire length is W, this would be W over 2. So, really, by the Pythagorean theorem, let's see, careful here. Maybe this wasn't the best choice for the y-axis to go downward from the top, but yeah, that is the best choice based on the density here. This distance right there is going to be r minus y. That's analogous to a y coordinate in an xy plane if you put the origin right there. By the Pythagorean theorem, really, r minus y squared plus w over 2 squared would equal r squared. When I say the Pythagorean theorem, I'm saying if I focus on triangle, that looked like this right there. The w over 2, which I kind of wrote over, is kind of like an x coordinate of the point. And the r minus y is kind of like a y coordinate. It's a base and a height. For that right triangle, use the Pythagorean theorem. R minus y squared plus w over 2 squared would be r squared. W over 2 is just this length right there, which is the same as this length. We can solve that equation for w. It's kind of a complicated looking equation, but it can be done. We can subtract that from both sides. We can then take a square root of both sides and then multiply by 2. Looks to me like our equation for w as a function of y should look like this. So it's kind of complicated. I did a few steps in my head there. I'll say it again. I subtracted this from both sides to put it over there with a minus sign. I took a square root, plus or minus, you'd want to take the plus square root because you want w to be positive. Then since it's a w over 2 that's there, I got to multiply both sides by 2 to get the 2 there. This should then be plugged in place of w before you let delta y go to 0 to get an integral. So it looks to me like the mass is going to be exactly the integral with respect to y as y goes from 0 when you're at the top of the shed to r, which is the height of the shed. It's also this radius. 0 to r, essentially of this expression, because this looks like a Riemann sum for this expression when you ultimately get it as a function of y. The L is constant, so you have an L there. You've got the delta of y, which is k times y. And then you've got this expression, 2 square root of r squared minus r minus y squared. If we were going to do that by hand, could it be done? I think so. I think it probably could be done with a substitution. I think here. Maybe if you let w equal this thing, maybe that's a good idea. Let me just see if it seems like a good idea if we were going to do it by hand. dw would be negative 2r minus y to the first power times negative 1 dy, just differentiating this with respect to y. The negative signs would cancel. Would that be helpful? You'd also want to solve this equation for y, or y dy. Multiply this out. Still have an r dy though. I'm not sure if that's the best approach or not, but for sake of time, we're not going to go further. Let's see if Mathematica gives us an answer. Integrate from 0 to r, L times, that's an L, not a 1, times k times y times square root of r squared minus r minus y squared dy. Let's see if we get an answer. Did I forget the 2? I did forget the 2. Sometimes Mathematica can do these kinds of things, sometimes it can't. It looks like it's, well, it's still running. It's still thinking. Okay, it did it. But yeah, that doesn't look so nice. And I'm wondering, because we have negative r to the 3/2 power, this could be a complex number. Oh boy. I'm not quite sure what to make of this answer. Okay? I'm not quite sure what to make of it. Mathematica may be sort of wondering, is r positive or negative when it writes this? I think I'll think about it after class, and maybe I'll summarize what I found about this next Monday.
I have a question about when you found the w to make equal y. Like, couldn't you have done just a proportion, like w over y equals 2r, because that's the base, over r when it's fully down at the bottom? Would that not work?
So you're talking about this picture here?
Yeah.
And you're saying what?
W over y would equal 2r over r, because the base at the very bottom is 2r, and then the height would be r.
So 2r, the height. Well, we're not dealing with similar triangles here. Yeah, I'd be a little careful about that. I will think about that after class. All right. What about the center of mass in the vertical direction? Again, maybe my choice of axes is not so good. The book says the density is proportional to the distance from the floor, which doesn't make any physical sense. Maybe more dense at the bottom. Maybe it results in easier integrals. What would the moment with respect to how I set things up be? in the vertical direction be? Call it delta capital M for this, focusing on this slice here. That would be the moment of that slice with respect to the floor, helping us find the center of mass ultimately in the vertical direction. Remember, the moment is the distance times the mass. That distance is really r minus y, and the mass is delta m, delta little m. This would be approximately r minus y times delta little m. Ultimately, we got delta little m to be this, and we plugged in W equals that. The total moment for the whole thing seems to me, based on this, should be approximated by essentially this, except, well, with this in for W, and also don't forget to multiply by r minus y. So it seems like it should be L delta of y 2 square root of r squared minus r minus y squared. And then don't forget to multiply by r minus y. Isn't that nasty looking? And again, this is k times y. Then we let delta y go to 0, and I forgot my delta y, didn't I? Delta y here. We let delta y go to 0 to get an integral. And the integral then for the total moment would be the same as this, except you'd have an extra factor of r minus y. Nasty. Okay? I don't know if Mathematica could do it or not. I could try and see. Assuming it could, then the center of mass in the y direction is going to be capital M divided by little m. Although that center of mass, with respect to this coordinate system, would be based on y equals 0 up here. And we get some positive value that would represent a downward position. Kind of complicated, okay? But I hope you see the thought process. It's easy to make a mistake. Okay? It's easy to be unsure if the particular coordinate system you have really is giving you what you want. Again, I picked it this way with y equals 0 there and positive y downward because it makes more sense to me to say the density should be proportional to that quantity. It gets denser as you head downward. That makes more physical sense. That's why I picked this way. And then it's just a matter of doing your slices in such a way that, in this case, the density is basically constant along within the slice. And then using these more basic principles like what is volume, what is mass, what is a moment, and going ahead and deriving these equations. It's a difficult skill, but it can be done if you're careful. Okay? But it takes practice. Let's do another example. Let's make it an easier example, actually. I'm going to assign number 13. Let me do one like number 13. I think I better not assign number 19, huh? I'm going to try to figure out, if the book really wanted you to do it as if the density was proportional to the distance from the bottom, do you get the answer in the back of the book? But again, that doesn't make much physical sense. So let me make up an example like number 13. Here we have a triangle. It's an isosceles triangle like the one we considered before. And it's put in the coordinate system. Here's an x-axis and here's a y-axis. This is 1, this is 1, or negative 1, and this is positive 1. You're told that the density is a function of x. And in the book's example, it's 1 plus x. Okay, let me just modify that a little bit. Let's make it 1 plus x squared. Interesting thing about the book's example is when the density as a function of x is 1 plus x, technically speaking, the density is 0 at the left corner because that's where x equals negative 1. Can that really happen? Well, It could be approximately, it could approach 0 as you approach that left corner. With this example, it's not going to approach 0. Well, and that's not going to be very interesting. It's going to be symmetric. Let's make it unsymmetric. So actually, this is going to be more like the book's example. And that's going to be a density that approaches 0 as x approaches -1. It's an area density, grams per square centimeter, say. What's the mass and what's the center of mass are our goals here. Do your slicing. Should you slice horizontally or vertical? What do you think?
Horizontal.
Well, actually vertical, because this depends on x. You want your slices to have the density approximately constant. I'm glad you tried that. If it was a function of y, then you'd want to slice it horizontally. Okay? And we are focused ultimately here on the x-coordinate of the center of mass. So take an arbitrary horizontal or vertical slice. We are going to have a little extra complication of the fact that these two lines would have different equations. So imagine a slice over here, a thin slice. Maybe I should give the piecewise function whose graph looks like a triangle a name. Let me call it f of x. It could be given a formula as well. In fact, this formula would be 1 minus the absolute value of x. Would be the formula for the function that looks like this, which is a piecewise function if you think about it in pieces. That would be 1 minus x if x is bigger than or equal to 0, and 1 plus x if x is less than 0. Think about that. When x is bigger than 0, this is a line with a slope of -1 and a y-intercept of 1. When x is less than 0 over here, you've got a slope of +1 and a y-intercept still of 1. But as one function, you can write it like that without a piecewise formula. It's going to just help me derive the formula for the integral more easily, I think. Take your vertical slice here, say of width delta x. What's the volume of that thin slice? It would be approximately, thinking of that as a rectangle, base times height. The base is delta x. The height is f of x. F of x times delta x. That would be the volume of the thin slice. What about its mass? Just multiply the volume times the density. The density is approximately constant on vertical slices. That's why we're slicing it vertically. This would be approximately delta of x times delta v, which would be then approximately delta of x times f of x times delta x. Adding those up would give you an approximation to the total mass. Letting delta x go to 0 in that summation would really, again, this is not, it seems like magic. It's not magic. It can be rigorously derived when your functions are nice. Letting x go to 0 gives you the mass for the total thin slice, the total triangle here, to be an integral of this function. You're adding up things of this form. It looks like a Riemann sum for that function that I circled. That would be the function you integrate. So the integral is going to be an integral of delta of x times f of x as x goes from -1 to 1. Look at the picture there. X varies from -1 to 1. As far as evaluating this integral goes, the fact that f of x ultimately has this piecewise formula means if you were going to do it by hand, at least, it'd be best to use the two pieces. It'd be best to break it up as an integral from -1 to 0, where on that interval, the formula for f of x is this one, 1 plus x. Add the integral from 0 to 1. On that interval, the formula for f of x is 1 minus x. And then you'd want to plug in this function, delta of x, in here and here, if you were going to do it by hand. And it wouldn't be too hard. You'd expand it out, you'd be integrating polynomials. Two integrals, add them up. On Mathematica, we can do it all at once. As one integral, I can type in the f of x function, 1 minus abs of x, stands for the absolute value of x. The delta of x, again, I'm taking to be 1 plus x cubed. And I'm integrating the product of those two functions from -1 to 0. So, that should give me the mass. Not the center of mass yet, just the mass. Can we take a guess as to what it might be? That's the density function. It varies as x varies. Does it have an average density? You might guess that the average density would be 1, actually. Because that would be the value of this function at x equals 0, and this function, graph it is, looks like this. That's a graph of delta of x as a function of x as you go from -1 to 1. Its average value would be 1. So you might guess that the average density of the sheet of metal here, if you're imagining it to be a sheet of metal, would be 1 gram per square centimeter. What's the area of this triangle? Oh, by the way, I should have done delta A instead of delta B, huh? Sorry if that was confusing. Not a volume, it's an area. If you feel confused about something, don't be afraid to raise your hand. That was confusing to you. The area of the triangle is 1/2 base times height. The base is 2, the height is 1, the area is 1. Will the answer be 1 times 1? 1? I'm not sure. Let's see. It is. How about that? The average density is going to be 1 gram per square centimeter. And the area is 1 square centimeter. Multiply those to get 1 gram. It is based on the symmetry of the situation. That's why I could guess that. Symmetry of this graph. This piece over here is like this piece, except reflected across the horizontal line at 1 and then across the vertical axis. The symmetry made me know that the average value of this function over this interval was 1. That's what allowed me to guess it. What about the moment? What would change here? Thinking about the thin slice there, we're thinking about a moment in the x direction with respect to the y-axis. The slab of metal is denser to the right than it is to the left. There's not symmetry with respect to the y-axis as far as it being equally dense. I just need the average density by the symmetry. I expect the x-coordinate of the center of mass should be further to the right. I would think so, yeah, because it's more dense over here. It should be a positive number. For the thin vertical slice, there's the approximate mass multiplied by x to get the approximate moment with respect to the y-axis. The approximate moment, use capital M, should be the mass times x. So ultimately, it should be the same integral with an extra factor of s. This was the mass there, that's a little m. Capital M should be the integral from -1 to 1 of x times delta of x times f of x. And I'm guessing that's a positive number. Okay, everything else is the same, you just add an extra factor of x. That's that. Really, it's not a distance, it's a position. When you're to the right of the y-axis, that position is positive. When you're to the left of the y-axis, the position is negative. But the integral should be positive, I think. Add an extra factor of x in here. You do get a positive number. Then the ratio, capital M divided by little m, the moment divided by the mass, is the answer. The center of mass. In this case, 1/15 divided by 1 is 1/15. That's the x-coordinate of the center of mass. What about the y-coordinate? We're not going to bother calculating that. It would be positive. For the y-coordinate, you would want to slice horizontally. Density only depends on x, though. That would still make it be tricky. We only talked about that in the case of a constant density. I'm not quite sure how the y-coordinate works out. I'll have to figure it out after class and I'll get back to you. But the x-coordinate would be 1/15. Center of mass is going to be somewhere along this vertical line. Getting close to break time. Ha! I'm too ambitious, I think, still. Let's do some work done problems. Okay, I think we're only going to get to work here still in lecture A and not get to force and pressure. We'll save that for lecture B. Let's do a fluid pumping example this time. Did a chain hauling example, and I hinted about what to do when you add an extra mass at the bottom. I gave you guys a hint for that last problem. Right? That extra mass at the bottom that you were pulling up with the chain went a constant distance. It was an anchor for a boat. You pretended it was like a point particle that you pull up a constant distance. And so you didn't have to figure out an integral to do the work done for that. You just take the force, which is the mass times g, times the distance. And that was the work for the extra anchor that you pulled up into the boat. You add that to the work done for the chain itself. Let's do a fluid pumping example. And to make it geometrically as simple as possible, we'll imagine that we are pumping out of a box shape, okay? Now I could make it different than a box shape. I could make it like a V shape, a trough shape. How do you pronounce that word? Trough, okay. A trough shape. I could make it a cylinder shape. It's going to be simplest if it's a box shape. Imagine you got a pool that's shaped like a box. Now, most pools are not shaped like boxes, but we're pretending. And the pool here is, let's say, 5 meters deep. 5 meters wide this way, and 20 meters long that way. Let's go ahead and assume you've got water filled to the top here. So water filled up to the top, and you've got, sitting along the side of a pool, you've got some sort of pumping system. I don't think I can draw it very well. I don't know what it would look like exactly. Pumping out water, I guess you have a hose in there going down to the bottom. Which makes the physics a little funny, but we're gonna calculate the work done to pump all the water out of the pool. And when you imagine trying to calculate this thing, you don't want to worry about individual water molecules and what happens to them. Okay? You don't want to think about the fact that to get down to the bottom of the hose, the water molecules all have to go to the bottom before they go back up. Evidently, it can be physically justified that you can think about the work done to pump all the water out without thinking about the water molecules. Okay? So it's just a word of warning. Don't think too literally in terms of what's actually happening. What you want to do is you want to imagine slicing this with horizontal slabs and imagining horizontal slabs of water of height delta y. So delta y is going to be the height of those horizontal slabs. I've been typically drawing axes in here, but you don't have to draw an axis. In fact, the book's examples, they don't typically draw axes. If I did, I'd start y equals 0 at the top and let it be positive going downward, because I'm going to imagine this distance right there is y. And to find the total work to pump all the water out of the pool, you first figure out the approximate work to pump the thin horizontal slab of water out of the pool, then add those up to get the approximation, let delta y go to 0 to get the integral. And again, you don't worry about what's really happening with the water molecules. Don't think too literally, okay? It just complicates things. And it evidently can be justified to think about it in the way that I'm going to show you without doing that. Work is force times distance. For the thin horizontal slab of water, essentially all the water in that thin slab travels the same distance upward against gravity. So the force is the weight of that relative to our gravitational field on Earth. And y is the distance. The weight of that, which you might call delta F because it's a force, of that thin horizontal slab is approximately the, well actually this would be an exact equation. It'd be the density of water times the volume of that water. If this density is a force density, a weight density, but it's not typically.
Okay, so that's a delta, not an integral symbol.
Now this is supposed to be a delta. You got to put g in there, the acceleration due to gravity, to make it a force instead of a mass. That, for water, is going to be 1,000 kilograms per cubic meter. Cubic meter of water, like this big in a box, has a mass density of 1,000 kilograms per cubic meter. G is 9.8 meters per second squared. This product gives you 9,800 what would it be? 9,800 newtons per cubic meter would be the weight density of water.
Would it be meters?
Multiplied by the volume in cubic meters, and you get the force, you get the actual weight. Does that make sense? What's delta V? You can write that in terms of delta Y. Again, I think we have an exact equation here. Let me just go ahead and replace it with 9,800 here. Delta V is the volume of the thin slice, 20 times 5 times delta Y. $100 times delta Y. So ultimately we get here 9,800 times 100 is 980,000 delta Y. That's the approximate, actually the exact weight of the thin slice of water. What's the approximate work to pump that thin slice of water up to the top of the pool? That's an approximation. Multiply this by Y. So Y times delta F, ultimately giving you 980,000 y times delta y. The total work done then is going to be approximately the sum of things like this, which will look like a Riemann sum for this function, 980,000 times y. And the limit as delta y goes to 0, it will be an integral. The total work is going to be the integral of 980,000 y as y goes from 0 to 5. The height of the pool there is 5. Let's see if we can do this. We're going to get 490,000 y squared. Y goes from 0 to 5. That'll be 490,000 times 25. I don't think I want to try to do that in my head. On the order of 12 million or so joules of work. 490,000 times 25, whatever that is, a little less than 12 million. A little less than 12.5 million, I should say. Somewhere around 12 million joules of work. Okay? Don't think too literally about water molecules. Evidently all this can be justified by a physicist. I'm not sure I can justify it in terms of the water molecules. Let's take our break now.